This is HRW910P058. We have a mass attached to a pulley. Now we're going to release this block from rest, and we want to know the speed of the block after it descended 50 centimeters starting from rest. And we're supposed to solve it using energy conservation principles. Treat the pulley as a uniform disk. So here's our pictures of what's going on. When they say use energy conservation principles, what we're saying is whatever energy it had when we released it, that's the same total energy in the system after it's fallen 50 centimeters as well. So, for instance, when we release it, all of the energy, well, we've got the gravitational potential energy of the block, and we've got the rotational kinetic energy of the disk, and we've got the linear kinetic energy of the block. Okay, now when we released it, it wasn't moving, so that becomes 0. The thing was not spinning, so that's 0. So basically, all the energy we started with was mgh. Ooh, that G is very, very funny looking. Okay. Wow. Okay. All of which we know mgh, so we could get a number for this. However, I'm going to leave it without a number for now because we're going to see something cool happen later. Now, after it's fallen, different color here, after it has fallen, the block is still up in the air, plus now the thing is rotating and the block is falling. Once it's fallen your 50 centimeters, I'm going to say that where it falls to, that's 0 height, so the potential energy of the block becomes 0, but now this thing is spinning, and rotational kinetic energy is 1/2 I omega squared. And this thing is falling, so it has kinetic energy, which is 1/2 mv squared. Okay? All of which should equal E, which we also know is mgh, so I'm just going to squeeze that over here. Okay, there's my V. That is what I want. I want to know how fast it is falling, the speed of the block. That's V, linear velocity. Okay, so I just need to plug in, I need to find out what I is, I need to find out what omega is and stick it in there, and then I can solve for V. Now luckily, this thing is a disk. We can treat it as a uniform disk. So in a uniform disk, the moment of inertia is 1/2 mr squared. So for this disk, that would be 1/2 big M is how they described in the problem, r squared. Okay, that's all nice. Omega is a problem. Omega, we have to think about this this disk. If you've got a piece of rope with something on the end that is falling with a velocity v, that means that right here, this point on the pulley has a velocity of v, a linear velocity of v, which means that the omega for this, or rather, sorry, here, we'll do this instead. For something that's rotating, a rigid body rotating, the linear velocity is omega times r, which means omega is v over r, which we want omega squared. That means omega squared is v squared over r squared. So if I put together, instead of 1/2 I omega squared, if I put this together, I get 1/2 I is this, 1/2 mr squared, and omega is this, or rather omega squared is this, v squared over r squared. The r squareds cancel out, and what I end up with is I can replace 1/2 I omega squared with 1/4, see those go together, mv squared. So that's what I'm going to do over here. I'm going to replace that. Replace. So now I've got mgh equals 1, oops, sorry. I'm replacing that. So it needs to be replaced. I can replace all of this with this instead. So instead, this becomes 1/4 mv v squared. This is still hanging out, 1/2 m v squared, little m. Okay, now I know little m, I know g, I know h, I know big M. The only thing I don't know is v, which is what I'm looking for. This is one equation, one unknown. I can solve it. I just need to do some algebra. So, well, let's do that algebra. We've got, I'm going to pull a v squared out on this side. So I get v squared times the quantity. This has a 1/4 m left over, big M. This has a 1/2 little m left over. Now I'm going to divide both sides by this whole chunk, and what I get is that v squared equals little m gh divided by the quantity 1/4 big M plus 1/2 little m. If I put in all the numbers for my problem, let's see here. Let's see, that's, oh, I don't think I have room. Dang. Well, I've got R. Oh, I don't need R. Notice R disappeared. It's gone, which is why later in part B, when it says repeat everything with a different R, the answer is the same, because R canceled out. We don't really care what R is. Okay, well, but we do have this. M is 20 grams, so that would be 0.02 kilograms. I have big M is 450 grams, so that'd be 0.450 kilograms, and then H is 50 centimeters, so that'd be 0.5 meters. Okay, so if I put all those in here, I get v squared is, you know what, I'm just going to put it in the calculator. And I get v squared is 0.8. That's weird, it's just 0.8. And then when you square root both sides, oops, why did I do that? You end up with the square root of 0.8 is 0.894 meters per second, and that is exactly what we have as our answer. And again, when you change the R wasn't in the equation, it canceled out, so nothing changes, you still get the same answer.